Can you hear me? Yes. Okay. So first, let me thank the organizers for the invitation to come and talk about my work, and also to thank all of you for preferring this session over the others. So the title is Weak Gravity Conjecture and Axion Phenomenology, but I would like to start from a somewhat broader perspective that has already been mentioned during the plenary lectures, which is what are the compatibility conditions of gauge field theories or effective field theories with quantum gravity. And I will try to review this topic with emphasis on what we can learn about real gauge field theories that applies to particle physics. So I will talk about some conditions, some of them very well known, like cancellation of gravitational anomalies, and some which have come up already in the lectures, like absence of global symmetries or constraints on the charged particle spectrum, in particular the weak gravity conjecture, and so on. So this all is framed in the idea of studying the swarm lab versus the landscape, as Kunrun and Oguri pioneered, and Oguri already mentioned in his talk. And as I mentioned, I will keep an eye on applications to particle physics and cosmology model building. So I will be focused on practical aspects of these general ideas. So what kind of constraints are we going to talk about, and which are the ones that have succeeded in giving real constraints for particle physics model? Well, the first one is really oldish. It's a cancellation of gravitational anomalies. So it's very well known constraint. In 4 dimensions doesn't seem very powerful, but one should not forget that if you assume that in the standard model you have the non-abelian structure of SU3 times SU2, and then an extra U1, which should be hypercharged, and you assume the non-abelian quantum numbers for the quarks and leptons, then the hypercharge assignments, which are these crazy numbers, they are fixed basically by gravitational anomaly cancellation. So it's a very powerful statement that one should keep in mind. So what can we say about the absence of global symmetries? Well, this follows from just general black hole arguments and so on and so forth, and has been derived in string theory, at least in perturbation theory, and seems to hold even non-perturbatively. What kind of implications does this have for string theory? Well, for the continuous case, it has been pretty much looked at, but in the case of, for instance, of discrete symmetries, is something which surprisingly has not been such much studied. So global symmetries are very important in model building, and in particular, if you go beyond the standard model and think about MSSM or things like that, they are very relevant to protect the protons from decaying in a matter of minutes, let's say. So you have to suppress certain operators, and the way to do that canonically is to impose some R symmetry or other kind of discrete symmetries that forbid those couplings. So insisting that these symmetries should be exact in the context of string theory, and demanding that they should be a gauge symmetry, so the anomalies have to be cancelled and so on and so forth, you can classify, for instance, in the MSSM, which are the discrete symmetries which are gauge anomaly free and have a usefulness like preserving the Yukawa couplings and preventing or forbidding certain higher dimensional operators that lead to proton decay. And there are interesting symmetries that come up this way, like R parity, which is like the most popular symmetry used in MSSM, but also there are other choices like baryon triality, which is just a subgroup, discrete subgroup, set 3 subgroup of a baryon number, basically. So if you try to study these symmetries, which are classified by just purely phenomenological terms and using cancellation of gravitational anomalies, in string theory, for instance, in D-brane models, you can do that. First, you have to realize how to implement discrete gauge symmetries in D-branes, and basically you do that by starting with a U1 center of mass on stacks of D-branes, and these U1s typically are eaten up axions and becoming massive by the Stuckelberg mechanism. There could be some discrete set and gauge remnant out of the original U1 symmetry, and this discrete remnant is preserved by instantons and any non-perturbative effects, even quantum gravity effects or whatever. So studying different models with intersecting branes and things like that, you can try to see what kind of these symmetries you can reproduce in realistic D-brane models, realizing the standard model or MSSM, things like that. And in fact, you can reproduce basically the same kind of field theory classification. So any consistent anomaly-free discrete symmetry that has been shown to be useful in this MSSM-like study can be realized in suitable D-brane models. Okay? So all of them belong to the landscape in a sense. Okay, in the non-abelian discrete case, things are much less studied. They are much more subtle. In a sense, you need some kind of non-abelian generalization of the Stuckelberg mechanism, and that's something that has not been developed yet, as far as I know. So basically, what we did in collaboration with some people in Madrid is to study axion moduli spaces, which are parallelizable. So you have several cycles fiber over each other in a kind of twisted torus-like fashion. So this is a scalar moduli space. And then you study gaugings of this moduli space by U1s in such a way that there is some discrete symmetry remnant, which is typically some discrete Heisenberg subgroup, because you're dealing with some twisted torus moduli space. So in this way, you can engineer some particular examples. So this is a very empirical study, some examples of non-abelian discrete gauge symmetries, and you can study what are the implications of these things. And in some cases, you see that they constrain Yukawa couplings in some deep-brain models or things like that. So again, they turn out to be useful, but we couldn't make any strong statement about classifications or whatever, because the thing was so confusing that we just managed to work out a few examples. So if you ask me, for instance, if there is a classification of which discrete symmetries can be realized in this way in string theory, I have no answer. I know that discrete Heisenberg groups can, and I can tell you the recipe, but if you ask me about, I don't know, discrete subgroups, ADA subgroups of SU2, I just don't know, okay? So there are many open questions that should be addressed, and presumably they will have some implications. So these non-abelian discrete symmetries are very often used also in model building, for instance, for people studying neutrino masses and things like that. They have all kind of crazy textures that they enforce by using different non-abelian symmetric groups or things like that. And there is, for the moment, there are no technical tools to just try to start implementing those things in string theory, because you don't know how to realize those symmetries. So there is a lot of open room to improve. So let me move towards the most perhaps quantitative statement about quantum gravity and particle physics, which is this weak gravity conjecture, which has already been talked about. So let me just review, for those of you not familiar with it, basic heuristic argument. The basic idea is to consider a theory with some U1 gauge symmetry and coupled to quantum gravity. So there will be some charged black holes which will evaporate. So if you consider extremal charged black holes, you're interested in allowing them to decay in such a way that they remain substremal. So the fact that they lose mass and charge in this particular way, because they emitted a particle with certain mass and charge, means that if this black hole remains subextremal, then this fundamental particle that was emitted in the evaporation should be superextremal. So the mass should be smaller than the charge in times the gauge coupling constant in Planck units. So you're guaranteed that if you try to make your gauge coupling very small, then there will be some surprisingly light particle compared with the natural cutoff of the theory, which is the Planck scale. And this light particle has to be included in your effective theory to be consistent. Okay? So in a sense, you can rephrase this whole story in terms of the cutoff of your effective theory if you then include these elementary fundamental particles. So the cutoff would be just suppressed with respect to the naive Planck scale by the coupling constant and perhaps other integral factors. Okay? And although this is originally phrased in terms of gauge fields, there are generalizations of these ideas that have been proposed for different p-form gauge fields. I will just focus on some examples like zero forms, which are in 4 dimensions. In 4 dimensions, they are scalars, axions basically, and 3 forms, which they are non-dynamical in 4 dimensions, but they are useful to discuss massive actions. The reason to generalize these ideas to p-forms is basically heuristically to think about T-duality in space-time directions. And this appears naturally in string theory, because if you have a brane that corresponds to a charged particle for some U1, then in some T-dual version, some type 2b version, if you start with type 2a, you will have the corresponding branes and gauge fields. Okay, so this weak gravity conjecture has turned out to be very useful to constraining models of axions. And this has been important in several studies in which there are scalars which roll throughout the transplanckian field ranges. This has appeared in models of single field inflation. So after the bicep 2 announcement that turned out to be not that great, there was a lot of activity in trying to build models with large gravitational tensor perturbations. And the way to achieve that in single field models is to have scalars traversing transplanckian field ranges. And more recently, there are other setups in which there are scalars which also have to traverse transplanckian field ranges, like the so-called cosmological relaxation models for the Higgs. I will mention that towards the end. So again, there is the general question of whether having the scalars traversing these large field ranges are consistent with quantum gravity. Okay, so let me just, well, in principle, this discussion was for general scalars, but it's natural to focus or restrict this discussion to the case of actions, because they're very special fields. So to discuss these trans-Planckian field ranges, you need scalars which have a sub-Planckian potential, which remains under control throughout possibly super-Planckian field ranges. And the simplest way to ensure that you have good control about the potential, including possible corrections and so on, is, in particular if you don't have supersymmetry, is to require that your fields have some additional symmetry. And actions, or action-like particles, in model building language, they are basically scalars which have some perturbative shift symmetry, which protects you to some extent against these quantum corrections. I will come back to this issue of which symmetry is the relevant one towards the end. And these scalars have some periodicity, so they are, you can think about them as phases of some charge scalar or something like that. So this shift symmetry is broken to just some discrete periodicity by different effects. So I will just distinguish two classes of effects. The first one appear in natural inflation and correspond to having non-perturbative effects that introduce some kind of modulation in your field space, which satisfies some discrete periodicity. The second kind of effects that break the periodicity to just a discrete one, or the shift symmetry to a discrete periodicity, are the action monodromy potentials, which are multi-branch potentials, which lead to monodromic effects, and I will discuss them towards the end as well. Okay, so the models of natural inflation correspond to situations where the only breaking of the shift symmetry is by exponential factors. They were introduced or motivated in this particular setup by these people to discuss inflation. So basically, you assume that there is some instanton coupled to this action. For instance, you can think about the QCD action and some QCD instanton effects that introduce in the one instanton approximation just some cosine potential of this form, where f is the discrete periodicity of your action. Okay. Now, if you want to have a trans-Planckian field range in inflation, you need this periodicity to be very large, so that you start rolling from the maximum of the cosine potential down to the minimum. And this demands that this f is much larger than the Planck scale. This is typically problematic in string theory. So anytime that you try to tune your parameters to achieve these trans-Planckian field ranges, or these trans-Planckian action decay constants, you end up at the edge of controllable regimes, like strong coupling or too small volumes, things like that. So in fact, this is just a reflection of a feature of quantum gravity that will follow from this weak gravity conjecture. So a natural way to avoid these issues is to go to multiple action models, and there are several attempts or several ideas to try to do that. The basic idea is to try to combine several actions and to find some kind of combination of them that works as some effective action with a longer decay constant or periodicity. Anyway, let's go to the basic idea and discuss what's the implication of the weak gravity conjecture to the action potential. So basically, the weak gravity conjecture demands that the weak gravity conjecture for the U1 gauge fields demanded that there were some electrically charged particles of a small mass compared with a charge. So for actions, the weak gravity conjecture demands that there should be instantons charged under the corresponding action with low enough or with too low action, so they contribute non-trivially to the potential, even though you didn't realize. And because they have larger charge than action, let's say, they have a factor of n here, which is the charge, which means that you're introducing higher harmonics in your potential. So you don't have just this nice cosine, but you have higher frequencies in your potential, which means that even though your periodicity, strict periodicity, is larger than the Planck constant or whatever, then the effective range in which you can roll down smoothly in inflation is smaller than the Planck scale. So this is the basic idea for single actions that already was in the paper by Kurrum and collaborators. What has been done recently by many people is to try to generalize and see how this works for multiple actions, for these other ideas that I was suggesting. And they are having a tough time as well. So models with multiple actions eventually have the same kind of problems in the direction of the effective action that has trans-Planckian decay constant. So the details of this discussion are still controversial, and more or less they depend on what kind of version of the weak gravity conjecture you believe in. So I will just restrict to the basic ones, which were already in the original paper by Arcani-Hamed and collaborators, which are the strong form and the mild form, but let me warn you that there are several orders, like the lattice, sublattice, Madison, so on and so forth. Okay, so the strong form means, in terms of the gauge fields and charged particles, that it is the lightest particle that has the larger ratio of charge over mass, and the mild form means that it is not necessarily so. Okay. So if you generalize this to arbitrary p-form fields and in particular to actions, the strong form would mean that it is the instanton that introduces the higher harmonics is actually the dominant contribution, so overrides the potential of the underlying cosine that you had, whereas the mild form means that you may have instantons introducing higher harmonics, but they can be subdominants with respect to the low harmonics. So you could have ripples which are not strong enough to spoil the slow roll. So which one of the two versions is the true one realized in the string theory or in the quantum gravity you want to work with, will dictate whether you can realize this idea of large field inflation in natural inflation or not. Okay, so there is an interesting debate on which version is realized in strings. And I think it's still ongoing because there are some counterexamples to the strong form, but there are specific features to them which possibly suggest one can do some refined version of the weak gravity conjecture or so. So there is food for thought in this setup. So in the remaining 10 minutes or so, let me move to the other direction in which one can try to achieve these trans-Planckian field ranges, which is axion monodromy. So the basic idea here is to consider actions which have a sub-Planckian periodicity, sub-Planckian decay constant. So the periodicity here is small compared with some Planck scale. And the way to achieve trans-Planckian field ranges is to have a potential which is multi-branched. It has several branches, like this. So if you move along one of the branches, you can move as far as you want. And yet the potential is periodic as a whole because of the periodicity imposed by the existence of the different branches. So this is the basic idea pioneered by Silverstein and Westphal, against in the context of inflation, although it's a general idea which can be applied to other setups. And this should be familiar to at least the holographic people, because this is a particular thing realized in the study of large and pure Yang-Mills theory when you study the energy dependence with a theta angle. The only difference here is that you're thinking about the theta angle to be a dynamical field, but that's kind of the basics of axion physics, if you wish. Okay, so something which is nice and came up a little bit later after this work is that the potential in this, for these actions, and in fact also for the models of natural inflation, is actually not so much protected by the perturbative shift symmetry of the actions, which in here is strongly broken by these quadratic potentials, things like that. Actually, the symmetry that is protecting the action potential is a dual three-form gauge invariance. And this is something noticed by Valley and collaborators in the context of the QCD action, in trying to reformulate it in terms of the two-form which is dual to the action in 4 dimensions. So the basic idea is to start with a theory of a three-form, which is a non-dynamical field in 4 dimensions, but nevertheless, you introduce it, and then you introduce this kind of Lagrangian. So you have a kinetic term for the three-form in terms of its 4-form field strength, and then you have this kind of a Stuckelberg-like coupling of a two-form, which is the dual of the action, and then this three-form. So if you take this theory, and well, this theory has some gauge symmetry, in which it's a standard gauge symmetry for the three-form, which acts inhomogeneously on the two-form. So there is a kind of Higgs-like mechanism in which the three-form is eating up the two-form, so it is eating up the action degree of freedom and making it massive. So it's a theory of massive actions, or in general actions with some potential. So in fact, if you dualize the two-form to the dual action, you realize that you have this kind of couplings, kinetic term for the action, kinetic term for the 4-form, and this kind of mixed topological coupling, which is a theory studied by Caloper and Sorbo, already in the context of axion monodromy. And now if you integrate out this non-dynamical 4-form, you realize that what you're describing is a massive action. And in fact, this can be generalized to arbitrary potentials. So the simplest quadratic term here produces a quadratic term in the action, but you can introduce also additional potential terms here, and you can translate those to a 4-form. Now, what is important is that in the original picture, this theory of the 3-form should be gauge invariant. So the only corrections that can appear here are powers of F4, basically. And this constrains what kind of potentials you can get in here. Okay? And in particular, it implies that they should be very much suppressed with respect to the Planck scale, so they are small corrections. So in basic action physics, without realizing that they have this dual formulation, you could have any arbitrary function of the action as long as it satisfies the discrete periodicity, but you could have huge crazy harmonics in between with enormous amplitudes. But these don't arise in physical realizations because they don't satisfy the fact that the action is dual to a 2 form which is eaten up by a 3 form. The corrections are in powers of this F4, and then they are very much suppressed with respect to the Planck scale. Okay, there are many discussions about whether weak gravity conjecture or other things in string theory can kill these models. Still, they are alive, although there are strong attempts to kill them. Okay, so many people are uncomfortable with Transplanckian field ranges. I can understand that. It's a matter of checking what string theory teaches us. Okay, there are very nice works by Palti where he constructs explicit models of action monodromy in terms of flux compactifications, and then some subtle renormalizations of the kinetic terms in this field space suggest that, in particular examples, so it's not a theorem, the field range is actually contracted when you include this correction to the field space metric. So even though it would seem at first that you have these Transplanckian field ranges, eventually you see that this parabola kind of close together. The opening here is much smaller, it's renormalized in such a way that you don't get Transplanckian. So it's a matter of seeing whether this is a feature of the particular examples he studied or whether it's more general. It's an open question. So in the last minutes, I wanted to discuss about the particular application of these action monodromy models, not to inflation, where they seem to work very well, but rather to a setup where there is trouble with them, which are these relaxation models. So these have had a lot of vigorous activity by many people in phenomenological model building, starting with this paper by Kaplan and collaborators. The basic idea is to try to find a new solution to the Higgs hierarchy problem. So the basic Lagrangian you start with is just the standard model Lagrangian coupled to some new degree of freedom, which is some scalar, which eventually will be an action because of the reasons I explained. So this action will have some potential, which will be monodromic or natural inflation-like or whatever. And then it has a coupling to the Higgs. So this term is the Higgs mass. In principle, you introduce here just some uncorrected one controlled by the cutoff of the theory. So it's not the physical Higgs mass, it's just the one that would be at the cutoff scale. And then this action couples as some effective mass to the Higgs. And then there are some kind of cosine potential for this action field like that. So the basic idea is that during inflation, although the inflaton is not here, during the inflation, this potential here is negligible. And basically this field, phi, is able to run in all possible ways and scan, canceling these all possible values for the Higgs mass. So until when inflation ends, basically the dependence of this scale, which is like the QCD scale on the Higgs mass via the quark masses, kind of kicks in, makes it this term kick in, and then stop the rolling or the crazy moving of this scalar in such a way that it happens when this quantity, the effective Higgs mass, is small. Okay, so it's a dynamical mechanism for adjusting dynamically the Higgs mass during inflation, such that when it ends in the place where the Higgs has the right mass. Okay, so there are many issues theoretically for this kind of models. For instance, to make this field an action really well doesn't satisfy periodicity, right? There is a linear coupling here and so on. But this is not a problem. You just make the model monodromic by adding many branches, and it is very simple to do so. You can take this scalar potential and put it in many branches, or you can reformulate everything in just some 3 forms, and it can be done. That's not a problem. But the problem arises because the coupling constant that appears here, which controls the coupling of the action to the Higgs, is tiny. It's something like 10 to the minus 34 GeV, right? It's an enormously small number. So what that means is that the branches in this action monodromy picture are very close together. Okay, roughly speaking, it's like in 1 GeV unit in distance. In field space, you will have 10 to the 34 branches. So clearly, there will be strong tunneling from one to the other. And in fact, you can apply the weak gravity conjecture to the 3 forms and predict that in this theory, there should be very light membranes. The tension of the membrane, as predicted by the weak gravity conjecture, goes like that, where this is the Planck scale, this is the action decay constant, let's say 10 to the 9 GeV or something like that, and this is G, this very, very small number. So these membranes are very, very light. And even though nucleation of these membranes during inflation is exponentially suppressed, they are so light that there is a competition of effects, and you can compute what's the effective cutoff for this theory. And instead of being extremely large, providing a solution to the hierarchy problem, you find that in the most optimistic way, I mean, in the conservative approximation, this cutoff scale is something like hundreds or thousands of TeV. So certainly not a great solution to the hierarchy problem. And the key of the issue is the lightness of the membranes predicted by the weak gravity conjecture, and the fact that they lead to a rapid tunneling rather than a slow roll. Okay, I should be concluding. It's clear that Transplanckian action decay constants are very much constrained by quantum gravity. In action monodromy, the situation is much less clear, and at the moment, it's not that all models are ruled out, but it depends a lot on what kind of system you want to describe. For the moment, for inflation, the models are still okay. For things like relaxation, they are pretty much constrained. They don't actually serve the purpose for which they were devised. So this is very interesting, and I find it very exciting that one can find applications of quantum gravity constraints which are relevant for new cosmological and LHC data. Thanks a lot.
Questions? If there are no questions, let's
Thank you.